All right, so let's take a look at a practical example on how we can calculate fault currents for a power system. So the power system that we're going to be using is going to look like this. So we have a source. So this right here is going to be my system, or the source in other words. And the data for this system is the following. So it's at 100 MVA base. And the positive and negative sequence source impedances are X1S, which is also equal to X2S, which is equal to 12%. And this system is operating at 115 kV. So in other words, again, the 100 MVA is the base, and the positive sequence is equal to the negative sequence impedance, and that's equal to 12%. Now this system is feeding a transformer. So I'm going to write it over here. And then that transformer goes to a bus, and we're going to call this bus X. And then we have a feeder over here, and that goes to bus Y. So the transformer data is going to be as follows. So let me write it over here. Transformer that has a base, again, of 100 MVA. And is a 115 kV to 34.5 kV transformer. And the transformer impedance is X sub T is equal to 7%. Now notice here that this is actually just a reactance, but that's typical for a transformer. Typically you would be given the reactance and then usually an X over R ratio, but for this example, just for simplicity, we're going to be using reactances only. Now this transformer is connected in a delta on the high side, and on the low side is connected in a Y grounded configuration. Now the impedance from bus X to bus Y through this feeder over here, and let's go ahead and call that ZXY. So the impedance between buses X and Y, again, that is going to be a feeder that's going to connect the buses X and Y. And so our fault is going to be at bus Y over here. So the impedance of the feeder, let me write it over here, feeder is going to be as follows. So it's on a 30 MVA base, and it's a 34.5 kV, of course, feeder, since again the low side of the transformer is 34.5 kV. And the positive sequence impedance of that, which I'm going to call Z1 XY. So 1 for positive and then XY, because this feeder connects buses X and Y in our system. So Z1 XY is going to be equal to 0.1 at an angle of 80 degrees. And this, of course, is in per unit, again, at a 30 MVA base. Now the zero sequence impedance of this is going to be equal to 0, or rather Z0XY. So the zero sequence impedance of the feeder between buses X and Y is going to be equal to 0.3 at an angle of 70 degrees per unit. So this is typical for an overhead transmission line or feeder. The zero sequence impedance is usually higher than the positive sequence impedance, and it usually has a lower angle than the positive sequence impedance. As we can see over here, again, the magnitude of the positive sequence impedance is 0.1, and the magnitude of the zero sequence impedance is 0.3. All right, so for our example, of course, we're going to have several steps, and let me move this up a little bit, and let's actually change colors. So let me change this to blue, and I'm going to say over here, step number 1 is going to be convert to a common base. Again, notice here on the top that the base impedance for the system and the transformer are both 100 MVA, but the base impedance, or rather the base power for the system and transformer are 100 MVA, and the base power for the feeder is at 30 MVA. So we need to convert everything to a common base, and since the system and the transformer are at a base of 100 MVA, what I'm going to do is I'm going to take that as a reference, and I'm going to convert the feeder impedance, which again is given with a 30 MVA base. I'm going to convert that to 100 MVA base. So we can do that using the following equation. So if we want to convert an impedance, so Z new is going to be equal to Z old. So again, this is converting from one base to another, and I'm calling the old basically the old base and new the new base. So Z new is going to be equal to Z old times the base power new over the base power old times the base voltage old divided by base voltage new, and this squared. Now for this example, because the base voltages are the same, we're just converting from 100 MVA to 30 MVA. This term over here is simply going to be 1. So again, this equation then gets simplified to Z old times SB new, so the new base, divided by SB old, so the old base. So for this example then, let me move this up again. I'm going to have that the positive sequence impedance of the feeder Z1XY is going to be equal to 0.1. Again, that comes from these numbers over here at the top. So 0.1, and I'm only using the magnitude because of course the angle is not going to change. So 0.1 times the new base, so we're converting to 100 MVA over the old base, which is 30 MVA. And this of course is going to be at 80 degrees. So the angle is not going to change, and this is in per unit. So this is equal to 0.333 at an angle of 80 degrees, and this is again in per unit. Now the zero sequence impedance Z0XY is going to be equal to 0.3, so again the magnitude times the new base over the old base, and again the angle is not going to change, so 70 degrees. This again is in per unit. So if we calculate this, we get that this is equal to 1.000, and I'm using 3 decimal places. So 1.000 at an angle of 70 degrees. This is again in per unit. Now step 2, and let me move this up, and let's actually switch colors to red. So let me write it over here. Step 2 then is going to be equal to, we have to draw the sequence networks. So draw sequence networks. And let me move this up again. And let's go ahead and draw the sequence networks. So the positive sequence network is going to look like this. So we have N1 over here, and then we have our source, so minus plus over here. This is going to be V equals 1 at 0 degrees per unit. And then we have the source impedance of the system. And let me actually redraw this. So the source impedance of the system, then we have the impedance of the transformer. Then here we have our bus X. Then we have the feeder. And then we have bus Y over here. So again, this is X1S, this is XT, and this is Z1XY. And let's actually go ahead and plug in the numbers. So this is J 0.12 per unit, so 12%. The transformer impedance is J 0.07 per unit, and the feeder is 0.333 at an angle of 80 degrees. And this is again in per unit. Now the negative sequence network, and let me actually switch colors so that we don't confuse them. So we're going to have for the negative sequence network the neutral over here and the same impedances. So we have the source transformer, we have the bus again here, and then the feeder over here. So this again is bus X, this is bus Y, And then this over here is x1s, which is again equal to x2s. So the positive and the negative sequence source impedances are the same. And again, that's equal to J 0.12 per unit. Then we have the transformer over here, xt, that's again equal to J 0.07 per unit. And then lastly, we have here the feeder negative sequence impedance. So Z1xy is equal to Z2xy is equal to 0.333 at 80 degrees. And this is again in per unit. Now let me move this up again and let's switch colors again so that we don't confuse them. So now we have to draw the zero sequence network. So we have the neutral over here, and then we have the transformer xt, then we have the bus X over here, we have our feeder, so this is bus X, bus Y, and then our feeder over here. So this is going to be Z0xy, which again is equal to 1.000 at an angle of 70 degrees per unit. Now I want to stop here and just note a few things again. Looking at this system here at the top, we have the system going from top to bottom. We have the system, then the transformer, then bus X, then the feeder, then bus Y. And then we calculated here in step 1, we converted the feeder impedances to per unit on a 100 MVA base. But we're given here at the top the impedances of the system and of the transformer at 100 MVA base. So those we don't need to change because they're already in 100 MVA base. So now in step 2, what we're doing essentially is we're drawing these sequence networks for all of the components in our system. So in our system, we have the system, so the source impedance, the transformer, then bus X, then the feeder, then bus Y. Now notice here again that the positive and negative sequence impedances, or rather the networks, look the same between each other. That's typical because again, the positive and the negative sequence impedances for the system and the feeder and the transformer are all the same. Now for the zero sequence network, notice that that looks different, and notice one more point, and that's that the source impedance is not involved in our connection. And the reason behind that is, again, as we discussed before, that the transformer has a delta connection on the high side. So the zero sequence network gets isolated from the system because of the delta connection on the high side of the transformer. That's why here for the zero sequence network, we only have the transformer and the feeder and not the source impedance. Again, that's because there's a delta connection on the high side of the transformer. And as we saw before, for delta Y transformers, we need to connect our zero sequence network like this, where basically the high side is isolated from the zero sequence network. Now for this example specifically, we're trying to calculate the three-phase fault current, or rather the fault current for a three-phase fault at bus Y. Now one more step that we should probably do over here is to simplify our sequence networks. So now we've again drawn the sequence networks, including the source impedance, the transformer impedance, and the feeder impedance. Well, we should probably simplify it a little bit just so that it's easier then when we move into the interconnections for the different types of faults. So what I'm going to do then is I'm going to simplify the sequence networks, and let me move this down a little bit, and let's switch back to, let's say, white. So I want to say step 3 then is simplify the networks. So simplify them such that they look like the following. So I'm going to have N1 over here, the positive sequence neutral. We have then the source, so negative, plus, and I have over here V. This is 1 at an angle of 0 per unit. And then we have here the positive sequence impedance. And then this is the point of the fault, which in our case is bus Y. So then we have the same thing for the negative sequence network. So we're going to have N2 over here. We have the neutral, and then we have the negative sequence impedance. then this right here again is the point of the fault, which for our example is going to be bus Y. And then lastly, we have the same thing for the zero sequence network over here. So we have the zero sequence impedance, and the point of the fault over here is bus Y. So this over here again is Z1, so the positive sequence impedance. This over here is Z2, the negative sequence impedance. And this over here is Z0, the zero sequence impedance. And of course, the currents that flow through these, this is going to be I0, this is going to be I2, and this is going to be I1. Now in this simplified network, basically Z1 is the addition of these three impedances over here. Z2 is the addition of these three impedances, and Z0 is the addition of these two impedances. So all I did from this step over here at the top to the simplified network at the bottom is I just combined everything together so that I have only one impedance to worry about. So again, in our case, Z1, let me write it over here, Z1 is going to be equal to X1S plus XT plus Z1 XY. And if I calculate that, that's equal to 0.521 at an angle of 83.630. So 83.630 degrees. And again, this is of course in per unit. Z2, we already know this. This is going to be equal to the same. So 0.521 at an angle of 83.630 per unit. And again, the reason why this is the same is because these simplified networks come from these networks over here at the top. And again, we know that the positive and negative sequence impedances for the system, the transformer, and the feeder are the same. So then over here at the bottom, then we can say that Z1 is simply equal to Z2. Now, lastly, for Z0, that's going to be equal to the transformer impedance, XT, plus the zero sequence impedance of the feeder. So Z0 XY, and again, if I calculate this, I get that that's equal to 1.066 at an angle of 71.287 degrees. And again, this is in per unit. So all I did here was I plugged in the numbers for X1, XT, and Z1, and same thing for the zero sequence over here. So I'm not gonna repeat that at the bottom, but essentially you can get those numbers from here. And again, using these equations over here at the bottom. So now we have a simplified network, or rather a simplified version of the sequence networks. Now we can do our interconnections based on the type of fault that we're trying to analyze. So I'm gonna say here, step 4, let me move this up again, and let's switch colors back. So let's do green for this example. All right, for this step 4, I'm going to say that's interconnect as needed for the type of fault. So as needed for type of fault. And also end calculate. So we'll get our results here. So again, for this example, we're doing a 3-phase fault. So I'm going to say for 3-phase faults, we know again from the previous lectures that for a 3-phase fault, only the positive sequence network is involved. So essentially we have a connection from here, the faulted point, back to the neutral of the positive sequence network. So I2 and I0 are going to be equal to 0 because those are not involved again for a 3-phase faults. So again, the reason behind that is that a 3-phase fault is a balanced fault. So we don't need to involve the negative sequence and the zero sequence networks. So then for 3-phase faults, simply we're connecting the faulted point, which in our case is this point over here, back to the neutral of the positive sequence network. And we can do an easy calculation for I1, which is the positive sequence current. And again, I2 and I0, negative sequence and zero sequence currents are going to be equal to 0. So let's move this up again. And essentially for a 3-phase fault, let me just go ahead and redraw that over here we have N1, we have the source over here, minus plus, V is equal to 1 angle 0 per unit. Then we have the positive sequence impedance over here, Z1. The current that flows through that is I1. And then we have a connection from the faulted point back to the source. So this, again, is the faulted point. So now we can just use Ohm's law. We know that voltage is equal to current times impedance, which means then that current is equal to voltage divided by impedance. So we can easily then calculate the positive sequence current I1. That's going to be equal to the voltage 1 and an angle of 0 per unit, divided by the positive sequence impedance, which we calculated over here at the top, over here. So that's simply equal to 0.521 and an angle of 83.63 degrees. That's in per unit. So we get then that the positive sequence current in per unit is equal to 1.919 at an angle of minus 83.630. Again, this is in per unit. Now again, I2 and I0 are equal to 0 per unit, because again, for a three-phase fault, the negative and zero sequence networks are not involved at all in the fault calculation. So now we have the positive sequence, negative sequence, and the zero sequence networks. So let me actually say one more step and we'll be done with this example. So let's switch back to red, let's say, and I'm going to say over here, step 5 would be convert to phase quantities. So, and again, we did this before, but we need to do 2 steps, or rather, I missed 1 step over here, convert to actual quantities, not to phase quantities. Meaning that we're going to go back from per unit back to actual quantities in amps in this case. So we know that the base current, and let's actually go ahead and derive this. So we know that 3-phase power is equal to square root of 3 of the phase to neutral voltage times the current I conjugate. This is the same as, or actually not V line to neutral, V line to line. So V line to line over here. So what I was going to say is that this is actually equal to 3 times V line to neutral times the current. So we know that our base voltage, VB, is in line to line. Usually for power systems, you're given the voltages in line to line, not in line to neutral. So for our case over here at bus Y, that's a 34.5 kV bus. So that's of course going to be our base voltage. So VB is then equal to 34.5 kV. And again, we know that the base power is 100 MVA. That's what we used for our base. So again, from this equation over here, we can derive the expression for the base current. So I'm going to say over here that I is going to be equal to S divided by square root of 3. Let me redraw this. So divided by square root of 3 times the voltage. And I'm going to say B's for bases. So the base current is equal to the base power, SB, divided by square root of 3 times VB. That comes from this equation, which again is the equation for the apparent power in a 3-phase system. And based on the fact that we're using the line-to-line voltage for the base voltage in our calculations. So in our case then, the base current is going to be equal to, again, the base power, which is 100 MVA, so 100 times 10 to the 6 divided by square root of 3 times the base voltage, which in our case is 34.5 So 34.5 kV, so times 10 to the 3. So we get over here then from this equation that the base current, and that's actually not a phasor, so the base current is equal to 1673.479 amps. So now we can convert I1, which we got over here in per unit 1.919, to actual quantities, meaning in amps. So we'll take that number 1.919 and multiply times the base current over here, and we'll get the positive sequence current in amps. So I1 then is going to be equal to 3211.406, and the angle of course is not going to change, so minus 83.630 degrees, and this is in amps. Now one more step, and let's switch back to white, and I'm going to say over here step 6. Now we'll convert to phase quantities if needed. So convert to phase quantities, and I'm going to say if needed. You might or might not need this. So now again, we did this before, but let's go ahead and do it again. The equations for converting from phase quantities to, or rather from sequence quantities to phase quantities, are the following. So IA, IB, and IC are going to be equal to the following. So IA is equal to the zero sequence current plus positive sequence current plus negative sequence current. The B phase is going to be equal to I0 plus A squared I1 plus A, and again I'm saying A, but some books use A for this operator over here. Some books use alpha for that. I'm going to use alpha instead. So IC then is equal to I0 plus alpha I1 plus alpha squared I2. So now we can go ahead and plug in the numbers. Again, we know that I0 and I2 are both equal to 0, because again we have a three-phase fault, which is a balanced fault. So then IA, IB, and IC, these are all phasors of course, are going to be equal to the following. So 3211.406 angle minus 83.63, and this is in amps, and then same magnitude for B and C. So 3211.406, 3211.406, but they're going to be balanced of course, so they're going to be shifted by minus 120 degrees and plus 120 degrees. So for B phase we have an angle of 156.370 amps, and for the C phase we have an angle of 36.37 degrees. And again, notice here that the currents all have the same magnitudes and they're balanced, meaning the angle between the A phase and B phase and C phases are 120 degrees apart. So B phase is lagging by 120 degrees and C phase is leading by 120 degrees. Again, I mentioned this before, but for these equations, we're assuming an ABC rotation system, meaning that B phase is lagging and C phase is leading the A phase. So as you can see, this is a very thorough example. Again, we have our example power system over here at the top, where we have a system, transformer, a bus, actually two buses connected by a feeder, and we're faulting the second feeder, so bus Y, or rather the second bus, so bus Y in this example. And we have a 6-step process for calculating the fault current for three-phase fault in this example. First step is to convert to a common base, so make sure that all of the impedances are on a common base. Second step is to draw the sequence networks. Third step is to simplify those sequence networks. Fourth step is to interconnect the sequence networks as needed for the type of fault that you're trying to analyze. In this case, we're doing a three-phase fault. Then step 5, convert from per unit to amps, so from per unit to actual quantities. And then lastly, step 6 is to convert back from sequence components to phase components. And again, this step is just optional if you need that. All right, so in the next few lectures, we're going to take a look at this same system as an example, but we're going to calculate the fault current for a line-to-line fault and a line-to-ground fault.